Students, let us continue our induction motors topic, that is induction motor parameters under running conditions. In last class, we have seen the construction of induction motor. What is induction motor and how this induction motor works, we have seen. Let us recall what we have seen in previous classes. The principle of working of three-phase induction motor and working of three-phase induction motor on no load and under load condition. Let us recall in details 1 to 3 minutes. Okay. So, here we have seen that three-phase induction motor consists of stator. Stator has the stator core, it is laminated internally, and we place the R phase, Y phase, B phase, R phase, Y phase, B phase and R phase, Y phase, B phase, the distributed three-phase winding R, Y, B, three-phase winding distributed 120 degrees apart. Now, I have placed my rotor inside. That rotor may be, for example, I can take a slip ring rotor. That means it is also having the winding, three-phase winding connected and star connected and taken out through the slip rings. Okay. Or you can assume whether you are going to assume one squirrel cage rotor or slip ring rotor. Okay, for simplification. Now, this is the rotor, this is the stator. Stator has the stator yoke, it is a mechanical protection, and stator core, it is made of the silicon materials, and it has stator distributed winding R phase, Y phase. And coming to the rotor, rotor has the two types. One is a squirrel cage rotor where there is no winding but copper bars inserted in a skewed slats. What is the benefit of the skewed? So, we know that by using the skewed, not so rotor slats are not parallel, just like the rotor bars are skewed some angle nearly. So, that is the angle. What is the purpose? Here to reduce the magnetic locking between the stator and rotor slats, and another benefit is to reduce the magnetic humming sound. That is why we prefer for the skewed slats in rotors. And we know that at the same time in wound rotor, so there is a three-phase winding is wound on a rotor, and R phase, Y phase, just like with the wave and lap winding similar to the stator, and is connected 3 inch in star, and 3 out terminals we taken outside, and for purpose of some adding some external resistance in the rotor circuit for starting purpose, starting torque purpose. Okay. So, this by using the slip rings we are going to use this one, that is why this rotor is the slip ring rotor. This is the squirrel cage rotor. Last class we have seen these all things. Now, So, in this class what our aim is that when 3-phase supply is given to our induction motor, for example 3-phase supply is given to induction motor, it produces a magnetic field in the stator, and this magnetic field produced is equal to the resultant magnetic flux is equal 1.5 times of flux produced by any one phase. And this flux is established in the stator, and not only in the stationary, it is moving in a clockwise direction, for example at a speed of synchronous speed. The synchronous speed is equal to 120 f by p. So, where f is the frequency of the supply and p is the number of poles designed for the machine. Now, this constant magnitude and rotating at a synchronous speed sweeps the rotor conductors. As for Faraday's laws of electromagnetic induction, then it becomes as a stator acting as a primary transformer winding and secondary act as a rotor. Now, we supply the 3-phase supply, it produces the flux links with the rotor. This is a secondary. Then EMF induced in this equal to E2, EMF induced is equal to E1. Similarly, when 3-phase supply is given to the stator, it produces a rotating magnetic field. This field cuts the stator conductors also. That is called, we can say, the E1. EMF induced in the stator also E1. At the same, the field links with the rotor conductors also. Then EMF induced in the rotor also E2. Then, as for Faraday's laws of electromagnetic induction, the EMF induced in the stator is a self-induced EMF, and EMF induced in the rotor is the mutually induced EMF. Then, this induced EMF in the rotor, so what will happen? Nothing but the current is flowing through this one. So, because if we are, for example, in case of the squirrel cage rotor, so what will happen? These rotor bars soldered at both ends. Now, it becomes the closed one. Then once EMF induced, that is equal to E2 in the rotor, then automatically just it acts as a secondary, then EMF induced in the rotor. So, this is a closed path. Then what will happen? Under circuit closed condition, the current will produced, because current will produce, that is we can say the I2 current. This I2 current flows, and the current is flowing through these conductors. As we know that whenever the current is flowing the conductor, it induces its own magnetic field around the conductor, and due to this one, it is also produce the flux of phi 2 in the rotor conductors. This flux produced in such a way that it is always cause of its production as per our Lenz's law. Then it will oppose the stator rotating magnetic field RMF, because what is the production of this one? Relative motion between the rotating magnetic field and stator conductors. Hence, what will happen? It has to reduce the relative speed. Hence, rotor, due to this current, the torque is produced in the rotor conductors, and the torque will try to move the rotor in clockwise direction, similar to the RMF, rotating magnetic field, to reduce the relative speed between the RMF and the rotor conductors. Hence, the rotor will starts rotate in the same direction to reduce the relative speed between these two. That is why it tries to catch the RMF field, but it never catches. Hence, the mechanical energy generated in the rotor. That is the basic principle we have seen last class. Now, what is different in this class? So, here our aim is to find that if induced EMF in the rotor, then how much EMF, that is EMF induced in the rotor is the rotor EMF. We can say this is equal to ER, we can say the rotor EMF. And if EMF induced, then current also produced, I2 current is produced. or we can say this is a IR, rotor current. If IR produces, then what is the power factor of this current? Next, what is the frequency of this one, rotor frequency? Because all parameters, here also are parameters. I want to note the what is the frequency in the rotor, what is the current in the rotor, what is the power factor in the rotor, and I want to note it. At the same time, what it will rotate in the speed, what is the torque developed in the rotor, I want to know. Whether what is the relation between these two, and already we know that the slip also we have seen. What is the slip? Slip speed, the relative speed. Okay, so I want to know the relation between these all parameters. Okay, it's a very easy and understand quickly also. Okay, let us see this one now. So what are the aim of in this class? So on completion of this period, you would be able to relation between slip, that is equal to S, you can say slip S, and frequency and EMF and current, that is called I, and power factor PF, and torque also. So we are going to interrelate relation between these all factors under standstill condition and under running condition. This is our aim in this session. Okay, what is the relation between the slip and torque? What is the relation between the slip and frequency? What is the relation between the slip and EMF and power factor, current, torque? All relations we are going to derive in this class. Okay, so now, and after that we are going to do some numerical problems for clarity. Okay, so as you know that this is the induction motor. So what is our aim to in this class? So when three-phase supply is given to this stator, the rotor will rotate, and the rotor conductors produces its own EMF and own frequency, own current, and own torque. I want to know these values when it is running under a different slip speed. Okay, this is our aim. Now you can see here, this is a one slip ring induction motor, three-phase induction motor. Now you can see this is a this portion just you neglect it, because it is the starting method of induction motor. By using the three-phase auto transformer, how you are going to start the motor, so we will see later. Now our aim is to, when three-phase supply is given to the stator, and what is the changes takes place in rotor, we are going to study. Okay, our aim is to, when electrical supply is given to stator, what are the significant parameters changes in the rotor circuit, we are going to analyze in this session. Okay, now say it. Now as we know that, and where let assume that E2 is a standstill rotor induced EMF for phase. Dear friends, here we are going to consider for phase values only. Okay, for phase values. If given the three phase values, you are going to convert in single phase by √3. Okay, so here E2, what is the E2? The standstill rotor induced EMF for phase, and I2, the rotor standstill current for phase. X2, the standstill rotor reactance for phase, and R2, the standstill resistance for phase, and F2, rotor current frequency at standstill. What is the standstill means? That means when rotor at speed is equal, rotor speed is equal 0. That means at initial position before starting the rotor, that is the standstill condition. Then standstill condition means, so this is the stator and this is the rotor, nothing but our transformer also. This is the primary condition, primary winding, this is the secondary winding. So similar this one under standstill condition, under rotor rotation is 0. Okay, so as already you known that, so what is happened here, the frequency of this one, what is the frequency, what is the already we derived that one, so relation between the speed, in this case whatever the frequency is given primary side, same frequency in the secondary side also, because transformer is a static device which can transform the energy from one circuit to the another circuit with the same frequency. So here also rotor at the speed is equal to 0 at standstill condition, then whatever the frequency 3-phase supply is given from the NPDCL people, same frequency induced in the rotor under standstill condition. So already we derived that equation also. If you require, so we will let us see that also. Okay. Now here last class what we have seen, so when rotor at standstill condition, so that means rotor, this is equal to stator and the stator winding, this is a rotor winding, let us just take it. Now once stator is given the 3-phase supply at the frequency of f. Okay, so we know that what is the relation when rotor at standstill condition, what is the 3-phase supply is given, it is a flux is produced, that flux is a synchronous ns. What is the ns? Synchronous speed. N is equal to 120 f by p. Here f is the frequency of this supply. Then what is the frequency? F is equal, we can write it, the relative speed, that is equal to, you can write it, F is equal to P number of poles into relative speed here, ns. So relative, we can write it the relative speed n, ns divided by 120. This is the first equation. At standstill condition, so we can write it, this is equal to, we can write it, this is equal to f, that is the normal frequency, at frequency at standstill condition, that is equal to number of poles and relative speed between RMF and rotor conductors divided by 120. Okay, so what is this one? So that is nothing but number of poles and this is equal to ns only. So n relative speed ns minus n divided by 120. Okay. So now what is the at standstill condition? The standstill condition, that should become to the 0 value. Then what is the formula? We got it. So P ns divided by 120, that is the same. So this one. Okay. Now if the rotating magnetic field sweeps the rotor conductors, it induces a EMF and produces the rotor current and it produces its flux, and due to this one torque is developed and the rotor will rotates. Now if the relative speed between the rotor conductors and RMF, what is value? Now let us assume the speed of the rotor, relative speed. So under condition running FR at running condition is equal to same P, and what is the relative speed? The relative speed is equal to ns minus n. Okay. So it is rotating at a speed of n. The relative speed is now ns minus n. Okay. Then divided by 120. This is a relative speed. Now initially the speed may be n rpm. In this case, it is rotating at a normal speed, that speed is equal to n. Now what is the relative speed? ns minus n. So, that is the relative speed. Due to the relative speed, it induces a EMF in the rotor conductors. Correspondingly, it produces the current, and correspondingly, it produces the torque. Due to the torque, it will rotate in the same speed of the RMF, that is synchronous speed, that is a rotating magnetic field. This is the second equation. So, and now write the simple equation. What is the first equation? We write the simple second equation by first equation. What is the second equation? Fr under running condition at a speed of n is equal to P into ns minus n divided by 120 all divided by, what is the first equation? Here P into, that is ns divided by 120. This is the first equation. Now 120 and 120 and P and P. So, what we are going to get it? Nr by, sorry, this is equal Nr Fr by F under condition. Okay. Now, so what we are going to get it? This is equal ns minus n divided by ns. So, this is nothing but, so what we have seen? This is nothing but slip. Now, so what is the equation? Fr by F is equal to S. Now, this is the frequency. That means, so frequency under running condition is equal to slip times of frequency under standstill condition. This is the equation we have seen in previous class also now itself. Okay. That means the EMF induced in the rotor conductors, the frequency is equal slip times of standstill condition produced frequency, that is the supply frequency. If you know the supply frequency, then we are going to calculate its rotor frequency at any slip. Okay. It may be 2% slip, 4% slip, any time slip we can calculate. So, this is the one parameters. Okay. So, this is one thing. Now, after knowing that, I want to know that what is the EMF in these conductors. So, EMF also. Okay. So, what is the EMF here? Now, after knowing the frequency, now let us do another parameter. In this case, now parameter is the EMF. Okay. So, what is the EMF of rotor under standstill condition, under running condition? Okay. So, both cases we are going to find it. Now, so you can see the same process. Now, you can see the same, once again you write it the figure. So, what is the figure here? So, you can write it. Okay. So, this is the stator and the stator winding. Okay. 3-phase supply is given, this one. Now, we are going to take the another rotor. So, rotor has rotor windings. Now, when 3-phase supply is given to the stator at a frequency of F and voltage of V, or you can say the E is given, the what is the EMF induced in this one? So, we already seen the rotor Fr induced in the rotors is equal to slip times of frequency developed at standstill condition. This one. Now, I want to know that what is the rotor induced EMF in the rotor when RMF sweep on the rotor conductors. As per Faraday's laws of electromagnetic induction, it induces a EMF. What is the EMF? At standstill. What will a standstill? So, same when stator act as a primary and rotor act as a secondary. then whatever the voltage is induced, that same voltage we are going to induce based on the number of turns. Okay. Now this is the V2, this is the V1 for example. So under standstill condition, under no rotation, what is happened? So we know that so EMF induced in the rotor is directly proportional to the relative speed, because so relative speed, the relative speed between the rotating magnetic field and the rotor conductors. Now relative, what is the relative speed? The RMF is rotating at a synchronous speed. Our rotors at standstill condition. So n is equal 0, and that is equal at the speed of nr. Okay, that is the relative speed, that is equal ns minus n. That is the relative speed. So that is equal EMF induced in the conductor directly proportional to the relative speed, ns minus n. Okay, this is our. So based on this one, we are going to write it. Now what is happened? So when at standstill condition at n is equal 0, first at 0 condition, no rotation or standstill, rotor speed is 0, standstill condition, that is called, what is called U2, that is equal directly proportional, we can write it directly proportional to ns minus n. In this case n is equal 0, then E2 is directly proportional to ns. This is the first equation. Okay. Now coming to the second equation. Once the torque is developed in the rotor, rotor is rotating at a speed of n rpm. Now rotor is n rpm. Then in this running condition, what is the EMF induced in the rotor conductors? That is, we can write the ER at one speed. We can say the ER2. We can write the ER2. Okay, so running at some speed, at slip speed, that is directly proportional to the same relatives, that is the ns minus n. Now speed has some speed rpm. This we can say is the second equation. Okay, this is the E2 is at a standstill condition, and ER2 at running condition, that is equal to ns minus n2. Now similarly 2 by 1, the second equation by first equation, we divide it. Then what is we are going to get? That is equal to ER2 at running condition divided by at standstill condition. E2 is equal to ns minus n divided by ns. So this is nothing but, what is this one? Nothing but S, slip. It's nothing but slip, that is called S. Now you can write it. So EMF induced in the rotor conductors is equal to slip times of EMF induced under standstill condition. So that means if you know the secondary EMF and under slip condition, if you know the what is the percentage of slip. Okay. So if you know that slip, you are going to find that EMF induced at that condition in the rotor conductors. This is a second parameter we have known. Okay. So and another parameter of same rotor. Now we are dear students, so we are going to analysis rotor parameters. We are going to postmart all parameters. What is the induced EMF? What is the frequency? What is the current? What is the power factor? What is the torque also? We are going to known by simple equations. These are all our basic formulas. Okay. So now coming to the relation between the rotor resistance, rotor reactance and rotor impedance. Okay, another parameters. As we know that, so this has Now, what is happened here? This is the stator and this is the stator 3-phase distributed winding, not concentrated winding. Now, we are going to see this one, our rotor. So, rotor, this is the whatever. This is our rotors. Okay, rotor has some rotor conductors or rotor windings. Okay, now I want to know that rotor has, for example, in case of the winding, in case of a slip ring induction motor. In slip ring induction motor, we are going to use the 3-phase windings on the rotor. Okay, and this winding, what is happened? This winding has its own resistance, own reactance, leakage reactance. Okay, and that means we can say this is the total jet impedance. Now, this rotor resistance, rotor reactance, rotor impedance may have any effect of slip. We have seen the frequency also, rotor frequency also slip times up frequency of stator, and EMF R2 also slip times up EMF induced under standstill condition. That means here the frequency parameter and EMF parameters, so it is a multiplication of the slip parameter. Similarly, I want to know that there is any effect of slip on resistance or reactance and impedance. I want to know in this topic. Okay, let us do this one. Now, already you know that. So, this is the winding R phase, Y phase, B phase, 3 windings. Let us take for phase values all. Okay, you take the R phase. In this one, R phase you take it. Now, I want to know that what is the values of this thing. Okay, so as we know that first resistance. So, what is the resistance? R is equal to first case 1 resistance. R is equal to rho L by A. The resistance of any conductor depends on the resistivity of the material, whether we are going to use the copper or aluminum, or length of the conductor, area of the conductor. So, it doesn't depend upon the any frequency or doesn't depend upon the any slip. Now, this resistance under standstill condition, under running condition, both are equal. That means this parameter does not change at standstill condition, at running condition. Simple. What are the resistance at standstill condition, at the 0 rotation condition is equal to the resistance under any slip condition. Okay, this is clear. Now, coming to the second term. What is the second term here? X. Okay, reactance, leakage reactance. So, as transforms has a same leakage reactance. So, now whether leakage reactance depend upon any factors, let us see. Now, case 2. In case 2, I am going to do another this one. Okay, you take the another color. Okay. Now, here what is happened? This is the this one, and it has some inductance L. Okay. So, that is equal to, we are going to ohmic value is omega L. What is the omega L? 2 phi f L, that is the ohmic value. Now, in this case what will happen? The inductance, that is going to XL. The leakage reactance is dependent upon the omega L, that is dependent upon the 2 phi FL. So, in this case you are going to see that the 2 is the constant, phi is the 22/7 constant, L is the Henry's and parameters. Now, what is the variable here? F is the variable, because under the frequency under standstill condition is F and frequency under running condition Fr. So, these are not equal both values. So, what are the values? Fr is equal to slip times of f. That means it depends upon the slip. So our parameter also depend on the slip now. Okay. So now what to do, how to, so here first case you can see it, that means here reactance also depend upon the slip or frequency. Now at standstill, similarly case first case, now at standstill condition and n is equal 0 condition, rotor speed is 0 condition. What is the reactance? That is called x, we can write it, what is the value, x2 at a standstill condition, that is equal to, what is the value, 2 phi f L. This is the first equation. Okay. Frequency is the rotor frequency is equal Fr, that is equal, we can write Fr, we can same. Now under running condition, at running condition, at sleep running condition at a slip speed, that is equal x, we can say 2 or running condition, that is equal, what is the value, 2 phi f r 2 running condition slip and L. Okay. So what is the value, we can write it, that is equal 2 phi. So here I can write it, instead of Fr, can I write it slip times of F2. Okay. So that is equal, here that is equal same, this is the F2 into L, this is the second equation. Okay. First equation only standstill condition, second equation at a slip speed. Now write the same 2 by 1, second equation by first equation. So what we are going to get, that is equal reactance under running condition divided by reactance at a standstill condition is equal to 2 phi, that is equal to, we can write the f s L divided by 2 phi f s, sorry, s L only. Okay. So no business of here, you can write it simply, you can write it 2 phi s in 2 phi f, you can write it f into L. So 2 phi phi L L f f. So we are going to get slip. That means here what we are going to concluded that, so reactance value under running condition at any slip speed is equal the slip times of reactance under standstill condition. This is the third term we known. Okay. The reactance under any running condition is equal to the slip times of reactance at standstill condition for phase values. Okay. So this is the thing. Now after known that, so resistance and reactance we known. What is the resistance? So under resistance under running condition is equal resistance at standstill condition only. Okay. And but reactance to or at a running condition is equal to reactance under standstill condition with the slip times. This is the two equations. Now based on this one, I want to know the impedance Z. What is the Z? Z is equal to R plus J of X L. Now so R is this one and X L is this one. Now automatically Z also based on the S parameter. Okay. So what is the value? Now Z, you can take another color. Okay. Z2 at standstill. Okay. Standstill under running condition, under zero condition, that is equal to R2 plus J of X2. This is the first equation. Okay. And same R under running condition at slip speed, that is equal, we can write it R2 plus J of S x2. This is the second condition. Okay. So, I want the relation between these two. So, you know the relation also, simple, this is the relation, this is one. Now, can I write the in the form of a diagram? You can easily understand what is the under rotor under standstill condition. Okay, rotor ohmic values. What is the ohmic values? R and XL and Z values. Okay, now I can see. So, what is this one? So, this is equal to, you can equivalent circuit, I can write it, that is equal E2, okay, EMF induced E2, that is AC. Now, we are going to get the R2 and we are going to write the inductance and we are going to equivalent circuit of rotor under standstill condition. This is the X2, this is the R2. Okay. Now, what is the values of this one? At the same time, I want to write it, this value, same thing. Okay, you can take the another color. We take the same under condition, but it is a slip speed. So, what is this one? Resistance. This is a reactance. Now, this is connected to the this one. Okay. So, here what is happen? The X2R, this is a R2, this is a ER2 under running condition. So, I want to know that what is the current in this one and I want to know that what is the current in this one. Both conditions I want to know. At the same time, I want to know that what is the PF cos phi at this condition. I want to know that what is the cos phi. Okay. So, if you know this ohmic value, if you know the supply, and I can easily calculate these values. Okay. Simple network theorems, network parameters. Let us do this in first case. What is happened here? So, you can simply write the equations. What is the I want the what is the impedance in this case? So, I can write it, the impedance. So, that is equal to Z. So, here Z1 is equal to R2 plus J of X2. No slip speed, because here slip is equal to what is the value? 1 at standstill condition, Okay. Then this is the value. What is the voltage? Voltage is equal what is the source? Voltage is equal to E2, simply standstill watt. Then I want the current. I is equal to, as per Ohm's law, V by ohmic value Z. Then what is the V voltage? That is the E2. Okay. Then what is the Z? Z is equal to R2 plus J of X2. Okay. I can write it in the form of, so E2 divided by under square root of R2 whole square plus X2 whole square. So, I am going to get this current value, that is called rotor current value and under standstill condition. Now, so as you know that, so basic formula. So, what is the power factor? Power factor we know that. So, this is the power factor. You know this is the XL, this is the R, this is the Z. Okay, the impedance triangle. So, this is the phi. I want to know that. What is the cos phi? The cos phi is equal to, we can write it, cos phi is equal to R by Z. Simply, you know the R, you know the Z. Simply substitute here. Okay. Then cos phi 2 under standstill condition is equal R is equal R2 only. Okay. Divided by, and Z is equal, what is Z? R2 whole square plus x2 whole square under square. So, we got it power factor, we got it current, and we got it everything in under rotor conditions. Okay. So, in this case we calculated what is the current, what is the power factor. Similarly, I want to know that these values. You can see what we have seen here. We calculated what is the voltage already is given. Now I calculated current as per the Ohm's law. So, V by Z is the AC circuits, that is equal voltage is equal to E2 is given, and by substitute Z is equal, I substituted these values here. Then I am going to get that E2 by these values, I am going to get this value. Okay, that is the magnitude of the current. I want to know what is the angle. So, cos, that is a power factor, phi is equal cos inverse of that angle. So, I know that from the impedance angle I calculated these values. Then what is the value? Cos phi 2 is equal R2 by this value. Now, I got whatever I required in the circuit under standstill condition. Now, we are going to calculate in this case what is the values of under running condition. This is the standstill, S is equal 0. Now, under running condition, what is the simple? We are going to calculate it. What is the R is the impedance X2? We are going to the Z2 at under running condition, that is equal R2 plus J of S X2. This already we have seen. Okay. Now, what is the current? IR2 rotor under a slip speed is equal to voltage by current. Sorry, what is the voltage by ohmic value? That is equal to impedance. Okay, that is equal to impedance. That is equal. What is the voltage? Here is given the ER2. What is the impedance? Impedance is equal ZR2 R2 plus J of SX2. Okay. Now, simply substitute these values. What is the ER2? S into E2. Okay. What is this one? R2 whole square plus SX2 whole square under square. So, this is the current I required. I got the current here. So, that is the slip times of E2 by slip times only. Okay. Now, I want to know the power factor. So, as we know the power factor cos phi 2, cos phi, okay. So, 2 R at running condition, that is equal R by Z. Okay. What is the R? A resistance R2. What is the Z? Simply substitute rotor R2 whole square, same values you are going to substitute, R2 whole square plus S into X2 whole square. So, we are going to get this is the power factor. Okay. Now, here power factor, so depend upon this numerator is the same, but denominator is the S times of this one comparing to the standstill condition. These are the two parameters. Okay. So, dear friends, do not confuse. So, just work out the simple circuit based on our circuits knowledge. We are going to analyze these circuits. Okay. Now, let us compare these two circuits with our 3-phase transformers and single phase transformer. So, that is okay. So, before going to this one analysis, so you maybe get some bore. Let us go to our PPT. Now, what happened? Okay. So, this all we see, you can see. So, here now we are going to compare this one. What is happened here? The value of the EMF induced in the rotor at standstill is maximum because the relative speed between the rotor and revolving flux is maximum. Now we are going to compare this one. So our induction, three-phase induction motor, okay, three-phase induction, this is a three-phase induction motor, three-phase induction motor. This is the three-phase transformer, okay. So now this becomes as a primary, so this becomes the primary, so sorry, so you can see here, so here, so what will happen, so this becomes the primary and here we becomes the primary and rotor acts as a secondary of the circuit, okay, just similar. Now what is the difference between these two? Here the difference between our induction motor and transformer is that, so here induction motor, the winding is distributed. So what is happened in stator, the winding is distributed in 120 degrees apart the three phases, whereas in this one, this winding is simply concentrated, simply we are at the R phase, Y phase with concentrated winding. This is a distributed 120 degrees apart, this is a constant. That is why when this three phase supply is given to the transformer, three phase supply is given to the motor, but in this case there is a magnetic field is induced, that induced EMF, the magnetic field is rotating at a synchronous speed, but whereas when three phase supply is given to the transformer, it induces a magnetic field, but it is not rotating at magnetic field due to the concentrating winding, okay, clear it. So now after that, so what is happened, so due to the here the air gap, there is a primary to secondary, what is happened, a primary to secondary, there is a iron is the one media through which the EMF, the flux produced in primary is going to the linked with the secondary. In this case what will happen, whatever the flux is developed in the motor is going to the rotor through the air gap, there is no iron core, this because it is a toroid, becomes a toroid. Now it becomes as a solenoid, that is a iron core is inside. So what will happen, so due to the air gap there is a flux leakage flux is more in this case, here leakage flux is less, hence this motor efficiency is less as compared to the motor efficiency of the transformer. That is the second point you have to remember, dear students, okay. So due to the air gap, leakage flux is more in this induction motor and leakage flux is less in case of the transformers, hence the efficiency of the transformer is more than 95%, whereas induction motor the percentage is efficiency is very less due to the mechanical losses due to the air leakage current is between the stator and rotor, air gap, okay. It may be less, but even that there is a air gap, that is the second point. Now coming to the magnetizing current, so what is due to the air gap, it requires the more current to produce the magnetic field, hence automatically magnetizing current is required in case of the induction motor is more, and here there is a iron core is has a catalyst to transform the primary to secondary flux. So hence here is magnetizing current is less as compared to the induction motor, okay. So these things you have to remember, okay. Now so as we know that here what will happen, so here it acts as a primary and it acts as a secondary. Now so when the rotating magnetic field is produced in the stator, it cuts the stator conductors also, that due to the stator conductors cuts, as per Faraday's laws of electromagnetic induction, the EMF induced the stator for phase, you can say that E1 as well, similar to the transformer primary, self-induced EMF and mutual induced EMF. Now what is the self-induced EMF in the stator due to the RMF? That is equal, we can write it, that is equal 4.44, and this is the winding factor Kw, winding factor W1, and because the distributed winding, and same frequency 1 and number of turns and the flux. This is the first equation. The EMF induced in the stator conduct test to the RMF is equal 4.44 K wind factor, that is a winding factor, F1 N1 5 maximum flux. That is equal first equation. Similarly, this flux EMF induced in the rotor also, that is equal EMF induced in the rotor, that is the secondary induced EMF equal to the same 4.444 and Kw2, that is the winding factor of the rotor. Rotor also distributed winding in case of slip ring induction motor. Then what is the frequency? So we know the frequency which changes, the Fr, that is the based on the slip F2, N2 and 5, that is the second equation. Okay. So now 2 by 1 equation or 1 by 2 equation, by first by 2 we are going to the E1 by E2 is equal, here what will happen? So all factors will goes. So here only similarly, so number of turns, this is the common terms will goes. Okay. Then what is happen? So changes only. So F1 here F1 here F1, but in this we can write it this S into F. Okay. So then we are going to write it this equation. So finally we are going to write it, that is equal to E1 by E2 is equal to, that is equal to N1 by N2 and at the same time Kw1 winding factor by Kw2 and into 1 by S, remaining factors are all equal. Okay. So this is a one similarity with this one. Okay. So these are the some parameters we know. Now you can see next. So what is the, when rotor starts running, the relative speed between the rotor and the rotating magnetic flux also decreased, as we have seen. What has happened? So once it is a rotating RMF, rotating magnetic field, under standstill condition it is the 0 position, n is equal 0 position, it is suppose example P is equal 4 volts, it is running at 1500 RPM. Okay, 1500 RPM. At n is equal 0, the conductors at 0, it is a 1500 RPM. What is the gap slip speed? Is a nearly ns minus n is equal to 1500 RPM, that is the slip speed. That is the, once nr increased, now n is equal 0, now ns minus nr is for example 1000 RPM, then what will happen? 1500 minus 1000, only 500 RPM, that is known as decreased values when rotor is increased. Okay. Now the rotor induced EMF, which is directly proportional to the relative speed, already we have seen. What is the EMF induced is directly proportional to the N2 minus N, that is the relative speed, proportional to the relative speed also, and it is also decreased when N value increases, and at the same time N equal to Ns, this rotor speed also 1500 RPM, then what will happen? 1500 RPM minus 1500 RPM, that becomes a 0, that is induced EMF in the rotor is becomes 0 as per Faraday's laws of electromagnetic induction. Okay. Hence for slip S, the rotor induced EMF will S times the induced EMF at standstill condition. Okay. Therefore under running condition, so what we have seen, so ER is equal S times of E2 at standstill voltage. The frequency of the induced EMF will likewise becomes the Fr is equal to S times of frequency at standstill condition. Okay. Now due to the decrease in frequency of the rotor EMF, the rotor reactance also decreases. This is also we have seen, and impedance also we have seen. Okay. So where ER and XR is the both are under running conditions. Okay. Now let us do the one or two problems for clarity. Okay. So we will see based on these parameters we are going to do the some problems. So what we have seen in this, just remember that. So here if I draw the curve between, here is the current or load current or torque, here we are taking the speed. Okay, so this is the speed. What will happen if load increases or torque? You can say this is the torque or current, because what is the formula? That's the torque is directly proportional to the E2 and I2 and cos phi 2. Okay, so we will see next class. Okay, that is the instead of we can write the phi, we can write the phi. We will see the next class. Now in this class we are going to see that so what is the relation here? You can see the relation. So here take the okay, this is we could take the, this is the torque or current, this is we take the speed. What is happen under 0? There is no load, speed is 0, torque is 0, and at standstill condition the speed is synchronous speed. So there is a synchronous speed under standstill condition. Once the torque increases, rotor rotates. Okay, rotor speed, that is the rotor rotates, then automatically, so what will happen? The relative motion between the rotor and synchronous speed increases. That is known as the relative speed. So there is a rotor speed, this is a synchronous speed. So what is the, initially both are equal. Once rotor picks up such a speed, the torque is developed such a way that T, torque is developed, it rotates, then the rotor will becomes at a speed. If the speed increases, the relative speed between these both are increases. At that condition, what will happen? At startingly ns minus n, that means is equal at startingly n is equal 0, then slip is equal, so maximum ns by n is equal 1. Initially the slip is equal maximum, that is the slip speed. Slip is the slip speed is this is the slip speed. Okay, ns by n. What is the slip speed here? Ns minus ns, that is equal ns only, that is the maximum. Once the speed increases, what will happen? The speed increases, this relative speed is decreases, so this value decreases. So this ns minus ns at 1500 rpm, at speed is equal 1000 rpm, then what will 500, so that value also decreases. Please, slip speed decreases but slip value increases. Okay, so you can see here it is going to increase. Okay, that is the slip. Okay, so you can see that one. So you take this side is the slip. So it slip this direction, slip increases when wear cap increases. Sorry, at standstill this is should be the, okay, you can, okay, we'll see later this one, no problem. Then let us do the one some problem base later. Now there is a one problem is given. What is the problem? There is a one induction motor is given. Okay, induction motor is given, then P is equal to 6, because here torque is not told to you, that's why I am going to some confusion. Okay, so I will explain later that also. Now let us do the one problem here. So what will happen? P is equal 6 volts, and at running at a speed of 2.5% of the slip is also given. A 3-phase induction motor, it has the 4 poles in the stator and it is running at a speed of slip speed of 2.5% is given. You want to know that what is the rotor speed nr in this condition. Okay, so we know that So we are going to find that P is given, and we know that 3-phase supply is given, and frequency is Indian frequency is 50 Hz. Okay, now we are going to find that what is the NR. As we know that, so NS synchronous speed is equal to 120 F by P. Okay, 120 F by P. Now what is the value is given? 120 is given, F is equal to 50 Hz is not given in the problem, but you know the frequency of Indian frequency 50 Hz. In case of the USA, you are going to substitute this value is the 60. Okay, now divided by number of poles. What is the 6? 6 ones are 6 twos are 2 5s are 1000 RPM. Okay, it is running at 1000 RPM. Now as we know that slip percentage, S is equal to percentage slip is equal to, what is the formula? So that is equal to NS minus NR divided by NS. Okay, now you know that this value also into 100%. For example, you take it. S is given. What is the percentage? That is a 2.5%. Okay, then it is equal to, so substitute this value 2.5%. N is equal to 1000 minus NR. I want to know that divided by 1000. Okay, into 100 we are going to, that's by 1000 we are going to that value. So you know this value, you know this value, you know only our unknown this value. Okay, then we are going to calculate. So calculate, so this value, what is the NR? NR is equal to, so this into this 2.5 into 1000. Okay, so that is equal to, and this you are going to get that. So NR here you are going to get, so NR we are going to get this minus my to find this one, I want this one now, minus you are going to that one. So here we are going to minus this plus, so nearly about 1000. Okay, so here we are going to get that 2.5% into this thing. So after that, so we are going to get it this value, then simply calculate this one. You are going to get that 975 minus plus 1000. So we are going to get that this value is equal to 25 RPM. That means the rotor is running at a slip speed of 2.5% is 25 RPM. Okay, such a way that you are going to calculate simple calculations, just whatever the values. Sometimes he will give the slip, sometimes he will give the NR also. You want to find that what is the NS. Sometimes both will gives, you are going to find the what is the slip. Okay, so you do the remaining simple substitutions of these values. Okay, so now do the another problem. So here another problem is also given. What is the problem? Problem is given. What is a 3-phase induction motor having a star connection rotor. So what is that one? Star connected 3-phase. So you convert single phase connection. Rotor has an induced EMF of 80 volts. Here what is the E2 is given for phase line to line, 80 volts is given. So you convert that by √3, you are going to get that value. Okay, so what is that one? 46.19 volts we are going to get the per phase value. Okay, now 80 volts is between the slip rings, that are face to face, line to line, at a standstill on open circuited condition. The rotor has a resistance and reactance for phase values. So here Z is value is given. What is the value? R plus J of X. So that value is given. What is the R? 1 ohm plus J of 4 ohms is given. Okay, this is the resistance and the reactance is given for phase value respectively. Calculate current for phase and power factor when. So you require the what is the current and power factor. Condition is given. What is the condition? First condition, slip rings are short circuited. So both slip rings are short circuited. Okay, slip rings are short circuited, that is just like connected star. Now another is slip rings are connected to a star connected rheostat. Okay, second case is star connected resistance, some extra resistance is added. Okay, so yeah, so I am going to explain clearly, don't worry. So once again, you can see a 3-phase induction motor having a star connection rotor has an induced EMF of 80 volts between the slip rings at a standstill on open circuit. The rotor has a resistance and a reactance for phase of 1 ohm and 4 ohm respectively. Calculate the current for phase, power factor when slip rings are short circuited and slip rings are connected to a star connector rheostat of 3 ohms for phase. Okay, a resistance of 3 ohms for phase is connected. So what is the meaning here? So you can listen, dear students. So go to our circuit diagram. So what is happened here? Stator is connected star. Okay, star connected. A induction motor having the star connection rotor. Rotor is star connected. Okay, anyway, we taken outside these 3 windings through our 3 slip rings. Okay, so now it is connected to the ear, and this connected here, this connected here, and is taken the output, this one. Here I have the another rheostat, that is equal another star connector rheostat, star connector. Now it has the different values. Now I connected, this is this one, I connected, this is connected this one, and connected, this is connected this one. Okay, now here what is happened? First case, this is the same shaft of this one. Is asking first case if this is shorted. Shorted means, so whatever this inductance value shorted in this case, you want to know that what is the current, what is the PF. First case. In second case is asking that this inductance values connected to some resistance here. Okay, so connected here. This is second case. So now in this case he connected the 3 ohms is connected. That is the second case. At this condition, what is the current, what is the PF, you want to know. Okay, so what is it given? A 3-phase induction motor has a stator has a EMF induced for phase, here is the 80 volts is given, and resistance also is given. It is each resistance value 1 ohm and reactance value 4 ohms also given, and this value is given, this value is given, and this value is given, here is a 0. Now you find that in this case, second case. Okay, let us case 1, when slip rings are shorted, that means it becomes this one. I want to note these values. Similarly, you calculate what is the here, what is the EMF induced here is given, the 80 volts is given line to line. So VL is given 80 volts. I want to note V phase, rotor E phase. Okay, that is equal, we can write it the E, or you can say that is equal E2. E2 is equal to 80 volts divided by root 3. So we are going to get what is the value, that is equal 46.19 volts, the per phase value. Now R is given, R is equal for phase value, what is the value, R is given, that we can say the R2 is equal 1 ohm for phase, and X2 I want to know that is given, the directly is given 4 ohms for phase is given. Okay, now I want to know the impedance value I am going to calculate. So simply we calculate the impedance value. So what is the impedance value? Z2. So simply Z2 is equal to and this condition. So R2 whole square plus that is x2 whole square under root. Then so 1 plus 1 square plus 4 whole square under root, I am going to get that is equal 4.123 ohms per phase. Okay, so I know these values, I got these values. Now in this condition, because it is not given any slip, dear students, slip is not given, so that means we are assuming that it is a standstill condition at initially. Now 4.12, then we know that as per the Ohm's law, so rotor current for phase I is equal to, so what is the voltage by impedance. So what is the voltage? Voltage is equal to, is given. So for phase we got it E2 by Z2. So E2 is equal to, we got it, what is the value? That may be 46 point, what is the value? So we are going to get that, simply substitute 19 divided by 4 point, this value 4.123 value. So we are going to get that value is equal to nearly 11.2 amperes. So 11 amperes flowing in the rotor conductors. Okay, now I want to know that power factor cos phi 2. What is the formula cos phi 2? R2 by Z2. I know R2 1 ohm. What is the Z2? So this value 4.123. So then I am going to get that is equal 0.243 lagging. This is a power factor. Okay, this is a power factor we are going to get it. This is a when two slip rings are under short circuit condition. Okay, now coming that, so that means what is the current? Current is equal 11.2 amperes at an angle of power factor. What is the power factor? Cos phi 2. Okay, so this is the current and at power factor. Now similarly we calculate the, in this second case, what is the second case? Is added the some resistance. Okay, then what is the value? Z2, in this case Z2 becomes to the R 1 ohm. Okay, so R2 plus J of X2. Here what is happened? Already this inductance is a 1 ohm and here is a 3 ohms. So total resistance is connected series. 1 plus 3 ohms is connected, that becomes the 4 ohms. Simply substitute here 4 plus J of X2. Okay, so only this is the changes and do the remaining all same process. Okay, here what is happened? Some external resistance added into the rotor circuit. What is the purpose? The high starting purpose, we are going to add some external resistance initially. After that we are going to remove. So we will see later that also how the torque is maximum when we are added that. Okay, so these are the, you do the, this is for your homework, you do it. Similarly in previous case we have 1, in this case 4. Similarly you calculate what is the current, what is the power factor. Okay, so let us summarize what we have seen in this class. Okay, so we have seen, so in this class we have seen that the relation between the slip, frequency, EMF, impedance, current, power factor under running conditions, and also we performed few numerical problems for clarity purpose. Okay, dear students, so there is a n number of problems in textbooks. You practice it. If you faces any problem, please ask in next class. Thank you for listening.